Greetings, we have this 2 by 3 matrix here. It's denoted here A sub 2 by 3, all meaning that the dimensions 2 rows, 3 columns. And this matrix, let's see, is it invertible from the right side? Because this is not a square matrix. So we can determine, invertible from left or right. Well, I sort of gave it away. Yes, it's a 2 by 3 matrix. It will be invertible from the right. And how do we know this? Well, there is this sort of theorem or some notes that we can relate to this. And by the way, we can go into this deeper in another one. But the main point here is that if you have rank equaling to the number of rows in a matrix, then it should be invertible from the right. So is it so? Well, in this case, if it has 2 rows, then the rank should be 2, and then it should be invertible from the right. Means we can find an inverse from the right side, like a matrix that we multiply by from the right side, whatever dimensions that has. And it will give an identity matrix, 1, 1, 1, like identity matrix, when we multiply the 2. Well, we should check that. We should check whether if this actually has rank of 2 under such conditions. If the condition is the rank of this matrix should equal to the number of rows, which is m. So in general, rank of A, of the matrix A should be m. M is the number of rows. So let's see. Well, we can do Gaussian elimination. So we can subtract once the first row from the second. We would have 0, 4, 2, and 9, 4, 5 in the first row doesn't change at all. We can also subtract back, sort of. So we would get subtract back the second row away from the first. So we have 9, 0, 3, 0, 4, 2. Alright, and we can also make it even simpler, divide by 2 the second row and by 3 the first row. But now it's clear. We have this column linearly independent from this one, and the third one is definitely linear combination of the first 2. So the rank the amount of basis columns are these 2. This third one is not a basis column. These 2 have a pivot. So 2 pivot basis columns with a pivot. The third one is not. So the rank is 2. And also another way to check it, we cannot find a 0 row. We cannot get to a 0 row by Gaussian elimination. We got to here or here, but we didn't get a 0 row. So the number of rows that are non-zero is 2. All the rows, there's 2 rows. So yes, rank equals to the dimension as far as number of rows. So we can invert it from the right according to this rule. All right, we don't have a wider view at this, but let's try to do that. Let's try to see what happens. So there is a general algorithm for constructing sort of an augmented matrix with the same number of rows identity matrix on the right, and sort of trying to get things from that. Now, by the way, I will sort of say in advance, the original matrix, this 2 by 3 one, will have an inverse that will be 2 by 3. And here we only have a 2 by 2 augmented matrix, and I would definitely recommend to first look at how these things are done for square matrices, a more general case, more universal, and so on. Because this is a little bit more specific. We will have to play around with the number of rows, columns a bit, because even though we have this augmented matrix with a 2 by 2 identity here, matrix, actually in the end the inverse will also contain another row that we'll add later. But we don't have any use in putting it there now. All we need is to get 4 entries, and the rest we'll take care of in a second. I'm not going to specify, we're going to see. So basically we're taking the matrix we had, we're looking for the inverse of it, and it's a very similar way. Till now, looks similar like usually with the square matrix. That's why I would recommend to know the algorithm regarding like normally square matrix, take an inverse of first. So I will take this 2 by 3 one we have, 6 entries here, and do the 4 entries extra, the identity matrix 2 by 2 on the right side to augment it. And now let's do row operations to basically, and again, I'm repeating it, but as I said, it was recommended to know, but in case you don't, actually what will happen here you see. You might be a little bit confused. Which entries will we want to transform? Well, what we want to do with the algorithm in order to get an inverse is you apply to the whole rows normal row operations, like the line is not there, right? So we have this 2 by 5 matrix. Like if the vertical line is not there. But what we want to get is these 4 left entries should become this identity 2 by 2 matrix. And whatever these 2 entries, the third column is, that won't matter. And what this will turn into will be the fundamental, well, we apply of course to the whole rows, these row operations. What these 4 entries, this 2 by 2 identity matrix on the right will become, that's the fundamental thing we want to put into the inverse. That's going to make the inverse. So let's see, let's do the row operations. We want this to transform to 1, 0, 0, 1. What these are, we don't care, and this will be important what we get at the same time. So let's try to do it. Again, we did this before, a few minutes ago, when we were doing Gaussian elimination anyway. So we're not just repeating the same thing, we could have as well kept that result. But we have to do it on this one, all row 1 anyway. So let's see. I will subtract again, first ones from the second. So the first one stays completely, 94510, and then subtract ones from the second, the first one. So 0, 4, 2, minus 1, 1. Now let's subtract the second one once into the first. So add the second one minus 1 times to the first one. So we'll get 9, 0, 3, 2, minus 1. And the second one stays. 0, 4, 2, minus 1, 1 stays. And this is 9, 0, 3, 2, minus 1. And now we go to this state, we're almost there, sort of. What I want is to just repeat. I want this square to become 1, 1, 0, 0. So what I'll do to the whole augmented matrix now is divide this by 9 to get a unit there, and this by 4, the whole row. So 1, 0, 1/3, 2 over 9, minus 1 over 9. Alright? And this will be 0 divided by 9, right? 1/3, 2 over 9, minus 1 over 9. Now 0, this is divided by 4, so we have a 1. 1, 2 over 4, 1/2, minus 1 over 4, and 1 over 4. So now we finally got an identity instead of what these numbers were. We got an identity here, and now, according to a similar algorithm, we're looking at it similarly like with a square matrix, this thing should be the fundamental part for our inverse. But let's make things a little bit, let's take a few steps back and let's look. A was 2 by 3, so we can multiply by some matrix B that will be, it has to share, the first dimension has to be same as the second dimension of the one on the left in this product. So it has to be 3 by something, I'll say 3 by 2. Alright? And so, that means that we will be multiplying by a matrix that looks more like this. That means 6 entries but more vertical. But we only had 2 by 2. We'll correct it in the way that we'll add 2 zeros here. So the similar algorithm like for square matrices, and let's add 2 zeros here. The same thing was sort of happening here. We got these 2 redundant entries and we're kind of ignoring them. We were happy that there's 1, 0, 0, 1 here, but we didn't care that some numbers, non-zero, non-1, stayed here. But let's test if it works. So predictably, for the inverse, we have first of all the 4 entries that we got in these places, and then as I said, we'll add the 0 row as well and see if it all works. So 0, 0 here. So let's see. Does this work? This 3 by 2 matrix? Well, of course, if we have a 2 by 3 matrix, we should multiply by a matrix that's 3 by something. So to be symmetrical like this, well, we want this, if this is 2 by 3 and this 3 by 2, we want the result to be 2 by 2 to give this. Because we're working with these outer dimensions to give the dimension of the resulting matrix of the product. If we're multiplying, of course, which we have not exactly denoted here. So this is supposed to be inverse, really based on what we got, these 4 entries here, and then adding the zeros below, and the A is here. So let's just write it out as if it's a product. Alright, that's what we're doing. So we multiply this by this. So let's see, is it really this? Well, let's check. So multiplying the first row by the first column will give 18 over 9, then subtract minus 1, and then plus 5 times 0. So this is 2 minus 1, which is 1. Great. Well, what about the second entry? Well, that should be the first row times the second column. So that's minus 1 plus 1 plus 0. So yes, it's 0. What about this entry? Well, that's second row times first column. That's 2 minus 2, 0 plus 0, 0. Good. And what about this last entry here? So second row, second column. Minus 1 plus 2 is 1 plus 0 is 0. Is 1. So yes, it works. Alright. So we got a right inverse to A. The right inverse is this matrix to this matrix that we had here. I also wrote it just once again here. This was A, and this was A to the minus first, the inverse to A from the right side.